Okay, well, I think it's about time to start. Welcome everyone to the first seminar in the Computational Sustainability Virtual Seminar Series. We are happy to offer this opportunity for those interested in computing and sustainability across the globe at small and large institutions alike. For this inaugural seminar, we have more than 80 nodes registered, and each node has multiple participants watching together. This virtual seminar series is being organized by CompSustNet with support from the National Science Foundation and Cornell University. My name is Doug Fisher, and I am the Director of Outreach, Education, Diversity, and Synthesis of CompSustNet. I and other members of the outreach team, which includes Carla Gomes, Christiane White, and Rich Bernstein, will be scheduling talks on computational sustainability regularly and posting them to the URL given at the top of this slide. During the webinar, you can ask questions through the question and answer facility on Zoom, which will be related to the speaker as time allows, perhaps to follow this, the presentation. If you have questions that you want to ask during the presentation, presumably a clarifying question, then use the hand raise mechanism to ask those. And when convenient, we will promote you to a panelist to ask the question aloud. If you have difficulties with today's seminar, make sure that you contact us and we will set up a test run for your node before future seminars. CompSustNet has several social media outlets, including Facebook, Twitter, LinkedIn, and the CompSustNet blog on our website. And you can see some of those about the middle of this slide. I'm going to turn this over now to Carla Gomes, who's the director of CompSustNet, and she'll say a few words and then hand it back to me for introducing our speaker today.
Hello, I'm Carla Gomes. I really just want to say a few words to welcome you all to this wonderful worldwide computational sustainability seminar. It's truly exciting to see such a high level of participation in this seminar. We have participant nodes in the US, Australia, Africa, and South America. And really, our mission and goal is to grow and expand this community worldwide, injecting computational thinking into sustainability issues, and at the same time, our experience is we encounter exciting problems from a computational perspective, and therefore we are advancing the state-of-the-art of computational sustainability. So really, our goal is to go worldwide and expand this community. So please, pass this information, the information about this seminar to your colleagues and friends who are interested in computational sustainability. Of course, I want to thank Doug Fisher for organizing this amazing, wonderful seminar, and Christiane White, say hi, Christiane, who really has, planned all the details and, all the logistic details of the seminar and is disseminating it worldwide. So thank you both for such an amazing job. Of course, I also want to thank our inaugural speaker, Stefano Ermon, for, giving this seminar, expanding on his paper that he recently published in Science. Congratulations, Stefano. That is just wonderful. I have to say Stefano was one of our first PhD students in computational sustainability, so it's really nice and exciting to see him pursue research in computational sustainability and taking it to new levels. But Doug is now going to formally introduce Stefano, and I just want to welcome you all.
Thanks so much, Carla. Yeah, I'll just add it's a thrill having everybody here. This is really breaking new ground in terms of global outreach, I think, and hopefully it will only grow in the future. Today's speaker is Stefano Ermon. He is currently an assistant professor in computer science at Stanford University. He's affiliated with the Artificial Intelligence Laboratory there and the Woods Institute for the Environment. He completed his PhD in computer science at Cornell. His research interests include techniques for scalable and accurate inference in graphical models, statistical modeling of data, large-scale combinatorial optimization, and robust decision-making under uncertainty. Stefano has won several awards, including 2 Best Student Paper Awards, 1 Runner-Up Prize, and a Mellon Fellowship. And as Carla mentioned, he's recently co-authored a paper in Science. So Stefano, it's all yours.
Hi, everybody. Can you hear me?
Yes.
All right. So let me share the slides. All right. Hi, everybody. I'm Stefano. As Carla said, I was one of the first PhD students to start working with her on computational sustainability back when the first NSF grant that really initiated the field started a few years back. And today I'm going to be talking about some of the research that I've been doing with my research group here at Stanford. So we all know that our society is facing some huge sustainability challenges. There are billions of people around the world that live in poverty, human activities, rising global temperatures, climate change are endangering the livelihoods of future generations. We know we're going to need new sources of clean and affordable energy, find ways to preserve biodiversity, both on land and in the oceans. And generally, we need to find ways to close the gap between developed and developing countries in a lot of aspects like education, gender equality, and many more. And I know a lot of the people that are attending this seminar, that are part of this community, the computational sustainability community, are working on these problems, and I think that's really exciting. We are working on some of the most important problems of our times, and I think that's really amazing. And these goals and these problems have also been recognized as being very important by the international community, by the United Nations. Towards the end of last year, the General Assembly approved the 2030 Agenda for Sustainable Development, and they identified 17 sustainable development goals. You can see them here on the slide. There are sort of like the big challenges that we are faced with as a society today, and that we should all be working on and trying to solve these problems. Now, it's great that we're setting these goals, but it's very important that when we set some goals for ourselves, we also have a way to measure progress towards these goals. So the goals need to be measurable. For example, if we take the #1 goal on this sustainable development list, the goal of ending extreme poverty, the one you see on the top of this list, it turns out that it's actually very hard to figure out how well we're doing towards achieving this goal. In fact, in order to be able to track the progress towards achieving this goal, to figure out whether policies are working or not, or to just help us in making decisions to make the situation better, we need data. And traditionally, the kind of data that governments and NGO have been using are surveys, national level surveys. And unfortunately, this kind of data is very, very scarce in some parts of the world, the poorest part of the world, like Africa. So you can see here a map of the African continent, and for each country, I'm showing the availability of national level surveys in the decade from 2000 to 2010. So on the left, we have a consumption and income surveys, so how much people earn and how much people spend every day. And on the right, we see asset surveys. So they would things like what kind of things people own, and like whether you own a refrigerator or how big is your house and things like that. But the striking picture here is that, as you can see, for many countries, there is no data available in the entire decade from 2000 to 2010. So you can see these countries are white, or or maybe there is only one survey. And so, as you can imagine, with this type of data, it's very hard to support research into poverty, figure out what are the drivers of poverty, what are the environmental, social, political drivers of poverty, and generally improve our understanding of this phenomenon and figure out whether policies are working and how well we're doing towards achieving this goal. So it's really important for us to figure out new and innovative and creative ways to come up with better data on this kind of development outcomes. So, for example, Give Directly is a NGO that has been working on facilitating direct cash transfers from developed countries to the poorest areas in the world. And in order to do that, they need to be able to locate where are the poorest villages, say, in a particular country. How can they find the poorest households within the villages? So for them, it's a huge challenge to be able to locate where these people live, find the location of the poorest people in the world. And recently, they actually came up with a very interesting new approach to solve this problem based on computation and based on data. Their insight was that there is a lot of information that can be extracted from satellite images. And for example, they came up with this approach where they said, well, if we look at an African village from a satellite and we check what kind of roofs the houses have, we can infer something about the socioeconomic status of the village. In particular, if we see that the village has many metal roofs, like the ones you see on the right, then it's more likely that the village is richer than one that has a high proportion of thatched roofs, like the ones you see on the left. And they developed a system based on sort of like traditional computer vision systems to do that. And this approach helped them a lot in cutting costs and making the operation much more efficient, because they could locate in a much more effective way where to actually prioritize their efforts and make their efforts much more effective in practice. Now, clearly, this was a clever idea, but if we look at what we can see in high-resolution satellite images, there is a lot more information besides the type of roofs that the houses have. So you can see on the left, there is something that looks like a busy shipping yard. You can see that you can almost count the number of containers, the cars, the ships that are there. So you could potentially infer all sorts of things about economic activities in that area. On the right, you see a more suburban area, and you can see that you can imagine that by understanding what is going on in this image and maybe sequences of images over time, you could infer all sorts of things about how the landscapes are changing, how cities are growing, or again, things about agricultural properties of the agricultural systems, or other kind of economic outcomes that we might care about. The good news is that this kind of data, remotely sensed data, is becoming better and better. The images that we get are becoming more accurate and cheaper. There are a number of private companies that are actually entering the market, even startups that are driving the costs down. So these days you can even get something like what you can see on the background, a high-resolution video taken from space. This is commercially available today and is provided, in this case, by a startup here in the Bay Area. So as you can imagine, there is a lot of information that is contained in these images and these videos. The problem is that this kind of data is very unstructured. We are basically dealing with images, raw bits, high-dimensional raw data. And the challenge is, how do we actually extract useful information? How do we actually extract actionable insights from this unstructured high-dimensional data? Like, it's maybe not too hard for a human to do that, but what we really need to do is we need to be able to develop algorithms. We need to be able to develop automatic systems that can extract this information so that we can really scale up these efforts and we can analyze very large amounts of images quickly and in an inexpensive way. So here is where deep learning comes in. You might have heard that AI and machine learning had some recent incredible success in a number of key conceptual tasks in computer vision, speech recognition, and so forth. And a lot of these recent successes are based on these deep learning models. What is a deep learning model? Well, in a deep learning system, these are essentially deep neural networks where we have layers of neurons that are stacked one on top of each other. And these machine learning models are very good at solving classification and regression problems based on high-dimensional unstructured inputs like images. For example, try to figure out try to classify images based on whether it's an image of a dog or a cat or a honey badger, like the one you see on the left. And the high-level idea is that instead of using handcrafted features like what people have been doing for a long time in computer vision, the idea is that we're going to use this deep neural network to automatically extract useful features for us. The idea is that the low-level features, the ones that are sort of the low-level neurons, the ones that are close to the image, will extract sort of low-level features like edges and corners, lines, things like that. These low-level features will be combined by the higher levels in the neural network to extract more abstract features like shapes, objects, and things like that. And then once we have these very powerful feature extractors, then we can use them to solve classification problems or detection problems, all sort of interesting perceptual tasks that we care about in AI. These systems are trained by backpropagation. Essentially, you show the network examples of images and the corresponding label. And when the network makes a mistake, like you show the image of a honey badger, but the network predicts it's a raccoon, then you can sort of find out what went wrong in that prediction. You can backpropagate the error. You can change the parameters so that the network will behave better and it will improve its prediction over time. The challenge is that in order for these deep learning systems to work, we need a lot of data. There is a lot of variability in the images that we see every day. You can see here some examples. And in order for these kind of deep neural networks to deal with all the variability that might be due to changing viewpoints, changing illumination, backgrounds, all sort of things that can change in an image, we need a lot of data. These networks typically have hundreds of millions of parameters, and to be able to learn these parameters effectively from data, we need a very, very large data sets, labeled data sets of examples that we need to provide to the machine learning model. Like, for example, ImageNet, that contains millions of labeled examples and have really been a key part of the success of deep learning models in machine learning. The challenge is that we cannot do this for our poverty outcomes. We don't have much data on poverty. And so this idea of sort of training a big neural network to predict interesting socioeconomic outcomes directly from images is not applicable. The reason we're trying to solve this problem, we're trying to predict socioeconomic outcomes from satellite images, is because we don't have much data about poverty. So this kind of approach of just training end-to-end a big neural network is not applicable in our case. So we need to come up with a different approach. And our solution here is to do something called transfer learning. The idea is that what we would like to do is we would like a mapping from satellite images to poverty measures, but we don't have enough data to do that. So instead, what we're going to do is we're going to consider a proxy output. We're going to consider a different but related task for which we have plenty of data. And by solving this task, we're going to gain some knowledge that then we can transfer to the original task of interest, which is the one that we actually care about, which is the one of predicting poverty measures from satellite images. So what kind of proxy measure are we going to use? Well, what we're going to do is we're going to use nighttime light information as a proxy for economic development. So here you can see an image of East Asia taken at night. And you can see that there's a striking difference between this part of the world, which corresponds to South Korea, and the northern part of the peninsula, where you see the North Korea country. And you can see that while South Korea is extremely bright at night, North Korea is mostly dark, corresponding to a much less economically developed country. So clearly, there is a lot of signal contained in these nighttime lights. And the idea is that we can try to exploit this signal, and we can try to use that as a proxy for economic development. The good news is that we have satellite images both during day and night for the whole world with fairly high resolution. And so what we can do is we can construct this proxy task of trying to predict the nighttime light intensity at a given location just by looking at the corresponding daytime image. For example, if you see, we can construct a very large training data set, like the one we were talking about, that we need in order to use a deep learning system. And we can train it because we have this label information because we're using this data-rich proxy. For example, we would like our model to predict low nighttime light intensity, where it sees an image of a forest, and when it should predict some high nighttime light intensity value when it sees that image below corresponding to a city. So what we did is we generated a very large training set based on this idea, and then we trained a state-of-the-art convolutional neural network to solve this proxy task. So mapping images, daytime satellite images, to the corresponding nighttime light intensity value. The idea is then to do transfer learning by effectively looking at the last layer of the network, which, as I mentioned before, corresponds to sort of high-level feature, high-level abstractions that are useful in order to solve this task of predicting nighttime light intensity. So the hope is that by using these features that I'm calling here F1 through F4096, that this feature in some sense summarize the image, and they contain useful information that can be used for solving the task of predicting nighttime light intensity, and hopefully then it will also be useful for the task of actually predicting poverty, which is what we actually care about. So are these features actually useful? Well, it turns out that they are. So we see here some of the features that we learned by actually solving this task of predicting nighttime light intensity from daytime images. Here I'm showing 4 of these features. You can see the one on the way to read this figure is that on the top row, I'm showing some images. On the middle row, I'm showing the activation map for some of these feature detectors that we learned by solving a transfer learning task. And then on the third row, I'm overlaying the first 2 rows so that you can see exactly what kind of things this feature detector is looking for in the image. Each column corresponds to a different filter, to a different feature extractor, and you can see that we've learned some semantically meaningful features. Like the first one is looking for, on the leftmost column, it's looking for urban areas. The second one is sort of looking for fields or greener areas. The third one is looking for bodies of water. The fourth one is actually looking for roads. You see how it's activating on the roads. And the key point here is that we never told the network what a road is, or what a city is, or what a lake is. It actually figured out that looking for these kind of features, like looking for roads, looking for bodies of water, looking for cities, is actually useful in order to solve this task of actually figuring out what's the amount of nighttime light intensity that we're going to see for that location. So here I'm showing more of these images and the corresponding activation map for some filters. And you can see that we discovered all sorts of interesting structure in the data. You can see that the network learned this filter that is looking for swimming pools in the bottom right. It's looking for houses with swimming pools. And probably that's because if there are many swimming pools in an area, that corresponds to a fairly rich area, and therefore it would have high amount of nighttime light intensity. You can see above that there is one filter looking for tall buildings that cast a big shadow. You can see one that is looking for trafficked roads and fields and many more. And again, the good news is that we didn't have to provide any labeled examples about all these sort of semantically meaningful features. We just discovered them from data by solving this transfer learning task. So now the question is, can we actually use these features in order to solve our task, the one we care about, which is the one of actually predicting poverty? It turns out that we can. What we did is we simply used these features that are extracted by the neural network, and we built a simple regression model on top of that to predict different types of poverty measures. We looked at both consumption-based measures, like how much people spend every day, and also assets-based measure of wealth, like what kind of things people own, how big their houses are, things like that. We used the limited available amount of data that is available today, provided by the World Bank and USAID, to train a model. And but because we already have good features, we don't need a whole lot of data in order to train the model. And it turns out that it does fairly well. It does capture a lot of the variation in the data, and it's very predictive. So these features that we identify in the data and images are actually very useful for predicting these kind of socioeconomic outcomes that we care about. So here you see a correlation plot where we're showing for each village for which we have actual data provided from the ground truth service. We are showing the correlation between the actual measured consumption for that location, so in dollars per capita per day on the x-axis, and on the y-axis you see what we predict for that location just by looking at satellite images. And as you can see, clearly it's not perfect because there is just some information and we cannot capture that, we cannot observe just by looking at images, but it's still doing a pretty good job. It's actually doing much better than any other method that is currently available. It does even better than previous techniques that are based on actually looking at phone metadata, like looking at who is calling whom and how much and for how long. Our method is actually giving more reliable estimates, and it's much less invasive. It doesn't, it's not as concerning from the point of view of privacy, because all we are using is publicly available high-resolution satellite images that are sort of available online. You can download and you can replicate our results easily.
Stefano, we have a question in the audience. Would you mind answering it now?
Sure.
Okay.
Well, I'm just curious, you talked about the features. How many features are you actually using in this regression plot?
So this one is using 4,096.
Okay.
Yeah. So 4,096, some of them, as I showed, are kind of meaningful, like they correspond to this kind of patterns that might be useful in the images. Some we haven't figured out exactly what they mean. So that's one of the problems with these kind of deep learning models. Interpretation can be hard, but they are predictive. They work pretty well at predicting the outcomes that we care about. Now, the good news about this is that it only requires these publicly available images that are available in essentially every corner of the world. So we could potentially just download images that cover an entire country, in this case Uganda, and then make predictions at each location and build poverty maps in a very scalable and inexpensive way. The challenge is that, as you can imagine, there is a lot of spatial structure in this kind of socioeconomic outcomes that we care about. You can see here that there is definitely a lot of correlation. If you take two locations that are close to each other in space, then they are more likely to have similar poverty values. So the question is, how do we actually model these kind of spatial correlations? And in order to do that, we're going to use something called a Gaussian process. So a Gaussian process is a probabilistic model that we can use to model an outcome, in this case R. You can see it on the y-axis as a function of an input variable, which we're going to think of as we're going to call x here, and sort of think of it as something representing space. Actually, we're doing two-dimensional things, two-dimensional maps, but just for making it easier to plot, we're going to look at a one-dimensional space variable and the corresponding outcome that is changing over space. So the idea of a Gaussian process is that a Gaussian process defines this outcome value, R of x, as a sequence of random variables, each one corresponding to a different location. And for any finite number of locations, the corresponding vector of outcomes is going to be distributed as a Gaussian random variable, which will have a given mean and a given covariance. And so the Gaussian process is fully specified by giving this mean function and the covariance, which will basically say, in our application at least, that if you take two locations that are close to each other, they are sort of more likely to have similar values. The idea is that this is a Bayesian approach. You start with a prior over how this function, this output value is a function of time, is distributed. And in this case, we're going to use a prior that has like a zero mean. You can see the black curve is identically zero. And then we're using some function for the covariance. Then the idea is that we're going to get some data. We are going to measure the, say, poverty values at different locations. So I'm showing them as red dots here. And then what we can do is you can compute the posterior distribution over the outcome of interest as a function of space, given that we have these measurements. And as you can see, this is some kind of interpolation that we're doing, so that if we take locations that are close to ones for which we have data, then we're going to get a value that is close sort of to the values that we actually have measured. And the nice thing about this model is that it also provides some uncertainty estimates. So you can see those blue curves, those blue envelopes around. This is the uncertainty that the model thinks it has on predictions made at different locations over space. Now, this kind of model has been used a lot in geostatistics. The challenge is that if we just use a Gaussian process to model say the poverty outcome, we're not going to be able to take the images into account. So in order to solve that, what we're going to do is we're going to use something that we call a deep linear GP model, where basically we're going to say that the outcome of interest is going to be given by a linear combination of the features that are given by the convolutional neural network and extracted at that location X, plus some error term, some residual term that is distributed as a Gaussian process, so that it can capture the spatial correlation that we know exists in the real world. So the picture to have in mind, it looks something like this. We have for each location, we have a neural network that extracts features, and then there's going to be an outcome, which is going to be a linear combination, shown in green there. It's going to be a linear combination of the features, the top-level features extracted by the neural network. And there is this Gaussian process layer that sort of couples all the outputs together so that they do exhibit the kind of spatial correlation that we would like to see. So it enforces the spatial correlation. And the good news is that you can still train this model end-to-end by maximizing the marginal likelihood, both as a function of the parameters of the neural network and the hyperparameters of the kernel that we use to define the Gaussian process. So you can sort of learn from data the kind of length scales of the spatial correlation that best fits the actual empirical observations that we have on the poverty outcomes. So in particular, you can still train end-to-end by doing backpropagation. We actually implemented it using TensorFlow, and so it all works smoothly, and so it is a very general technique. The other nice advantage of this Gaussian process formulation is that it allows us to capture uncertainty on the predictions that we make. So for example, if we have two locations for which we don't have labeled data, for which we want to make a prediction, we can use the Gaussian process not only, or this deep Gaussian process, if you want, not only to make a prediction by basically looking at the black curve corresponding to the green triangle, but we also get a sense of the uncertainty that we have for that prediction that we make at that location. That's essentially is the width of that uncertainty envelope. You can think of it that way. So if we have these two locations, for example, we know that when we're going to make a prediction, we know that, for example, the one on the right, we are less uncertain about the one on the right than the one on the left, because that green bar is a little bit smaller. The good news about this is that now we can actually use this approach in a semi-supervised fashion. The idea is that we can try to fit both the neural network parameters and the hyperparameters of the GP, not only to maximize the fit of the data points for which we have labels, for which we have measurements, like for which, for example, we have survey data, but we can also try to find the parameters that attempt to minimize the uncertainty that we have at these green points, the unlabeled ones, the ones where we actually want to make prediction on. So for example, we could try to, because effectively what the neural network does, it's finding an embedding of the images over which we define this Gaussian process. So we can sort of play with the position of these green triangles in this embedding dimension, each of X. So for example, by changing the parameters of the neural network, we might find a different embedding that puts these unlabeled data points closer to the ones for which we have labels. And at that point, the uncertainty becomes smaller, which we think is going to be good, because what it means is that on expectation, the model is going to make smaller mistakes on these unlabeled data points. So here is another picture of how this might look like. If we jointly train the neural network, the Gaussian process, in order to both maximize the fit of the labeled data and minimize the uncertainty on unlabeled data, what the neural network does is it's looking for an embedding that will make unlabeled data points look more similar to labeled data points. So you can see the difference between these two plots on the left and on the right. You can see that on the here each dot corresponds to a data point. Some circles are unlabeled, the triangles are labeled. I apologize, I think before I had the other notation, but it doesn't really matter. You can see that when we augment the learning process with this additional term that is sort of trying to minimize the uncertainty on unlabeled data points, the result that we get on the right tries to put all the points closer to each other. See, the triangles and the circles are closer to each other with respect to what we have on the left. And in some sense, you can think of it as sort of trying to identify features that are also going to be useful, that are also present in images and in locations for which we don't have labeled measurements, because we think that those features are going to be more useful when we actually use the model to make predictions at those points. Turns out that this approach works quite well. We've shown some improvements here in some standard machine learning data sets from UCI. So here I'm showing as a function of the number of labeled examples that are available, the root mean square error, so how big are the mistakes that we make by fitting a model. As you can imagine, all models get better and better as we have more training data, as expected. And here I'm showing in blue a model that is just a neural network. Purple is the neural network plus the Gaussian process, where the Gaussian process where the neural network is kept fixed, and you just train the Gaussian process on top of the neural network. DKL in green, the deep kernel learning, jointly trains the neural network and the Gaussian process at the same time. And then we have this semi-supervised DKL in yellow, which also tries to minimize the uncertainty at new unlabeled data points. As you can see, the error of that yellow curve is smaller. So the model is able to make use of these unlabeled data points to find a better embedding, a better feature map that actually will work better when you actually use the model on new examples that you haven't seen before during testing. This turns out to work well also for the poverty mapping problem. We've been able to actually improve the performance even more in that case. And we can finally use the models to actually generate poverty maps at scale without only using publicly available data. In this case, what we do is we take a country, in this case Tanzania and Uganda. We download images that cover the entire country, and then we feed them into this machine learning model, making predictions at each location. And so the nice thing is that we can come up with these estimates for locations for which we don't have any ground truth data. All we need are satellite images, which is a huge advantage over traditional survey methods because it's much cheaper, it's more scalable, and it's also safer. Like we were talking to people at the World Bank, and it's a huge problem to do surveys in countries where there are conflicts. Like they have their people that go around taking the surveys being kidnapped or killed, and so there are many countries in which they cannot even and they cannot gather any survey data because it would just be too dangerous. So this approach, on the other hand, only uses satellite images, so it's much more scalable, much cheaper, and still reasonably effective. We did it for several countries. We see before Tanzania and Uganda. Here I'm showing other two countries, Malawi, which is one of the poorest countries in the world. You can see that our predictions indeed predict that most of the country is actually pretty poor. And you can see on the right Nigeria, which is quite different. They're pretty far away. One is in Western Africa, one is in Eastern Africa. And we can see that the prediction that we get in Nigeria is quite different. We see that there is a lot more variation, and the southern part of the country that is more rich in natural resources and more developed is much greener, and that is actually picked up correctly by our model, which it makes predictions that the southern part of the country should be richer than the one than the northern part of the country. So we've also tried to see what happens if we actually try to train a model in one country and evaluate it in a different country. So the way to read this plot is that I'm showing the performance in terms of R square, which you can think of it as how well we can fit the data in cross-validation as a function of which country you train on and which country you evaluate on. And as you can see on the diagonal, we get the biggest crosses, which means that we get the best model, and that corresponds to models where we train and test in the same country. So if you want to build a model for Malawi, the best thing you can do is to actually use data from Malawi, train in Malawi, and then test in Malawi. But if it so happens that you don't have any data for a particular country, you can still try to use maybe a nearby country and try to train a model there and then evaluate in a different country. And you can see that while it doesn't do as well as training and testing in the same country, it's still doing reasonably well. You can see that the R squares are still pretty good. And so that's important because this allows us to make predictions in countries for which we don't actually have any survey data available. One of the things we're doing, for example, is providing the World Bank a map of Somalia. That's a country for which they don't have any ground truth data. And so we've been trying to build a model on Ethiopia, which is nearby and for which we have some ground truth data, and then testing in Somalia, so that we can get reasonably good estimates. So the hope is that these models will actually be useful for decision makers to make better decisions and try to help them solve this big problem of eradicating poverty worldwide. For a long time, Africa has been shrouded in darkness. You can see in the literal sense, a lot of the country is actually dark at night. They don't have access to electricity. And so when you look at it from the satellite at night, it's completely dark. More importantly, the country has lagged behind, the continent, the entire continent has lagged behind on all sort of development outcomes in terms of healthcare, education, economy, and so forth. And so we really need better data sources to help and try to turn this tide and improve the situation. Our models are clearly not perfect. There is a lot of room for improvement. All our data is available online, and you're welcome to play with it and try to see if you can improve. We're sure that there are better ways to do it. And I think it's a great application. It has a lot of potential impact to really help us make better decisions and help both NGOs and government organizations in dealing with this problem. We've had a lot of success already with our model. Opportunity International, for example, is an NGO working on trying to end global poverty by creating jobs in poor areas of the world. They reached out to us immediately after we published the paper, because they wanted to use the data into their system, and they've actually been able to do it. I got an email last week from one of their employees, and this is a screenshot he sent me showing how they integrated our predictions into their system. And you can see this is Uganda. You can see the branches that they have in the country and how they're trying to use this to make better decisions and make their operations much more effective in practice. We've also had a lot of interest expressed by bigger organizations and foundations like the Bill Gates, the Gates Foundation and Bill Gates. The World Bank, the Department of State is very interested in coming up with these kind of maps, especially also for health-related outcomes and food security outcomes. And more recently, also the World Food Program has also, we've recently started a discussion with them to see to what extent they can use our data for their kind of applications. So this brings us to the second part of the talk, which will be a little bit briefer on food security. Food security is another huge issue. It's actually the number 2 goal on that list of 17 goals for sustainable development, ending extreme hunger. There are still hundreds of millions of people around the world that don't have enough to eat, and the problem is getting worse and worse because the population is booming, and there is an estimated 2 billion more people to feed by 2050. This is another very promising domain for using computation and information technologies to help address some of these challenges. There are several of them that I'm gonna present here. I think a big one that I think our community should be thinking about is how to use similar ideas like the one I described here. So finding more innovative ways to use unconventional data sources, cheap, passively collected data sources to track food security outcomes globally. So try to figure out how well we're doing towards these 2030 agenda goals. That's another domain for which we don't have good data. So there's a lot of room for improvement for coming up with clever ways to come up with estimates for these kind of outcomes. And also locate and prevent food crises. That's another big problem where there is a lot of potential for using information technologies and new data sources. We recently we're starting a new project on this with Facebook. We're going to try to see whether we can use Facebook data to make these kind of predictions, identify food crises, try to predict food prices, and try to see whether we can say something by using social media data about hunger and related problems worldwide. But this is just started. There is a lot more we can do in this space. The other big problem, I think, is agricultural monitoring and forecasting. We need better models to predict food production and demand so that we can predict, again, food crises, and we can take actions accordingly to improve the situation. Real-time monitoring of food prices, that's another big thing that people at the World Food Program care a lot, and I think there is a lot of opportunities for using CS and information technologies ideas in that space, and also try to understand how climate change will affect agricultural production and how to best cope with the changes that we know are going to take place in the future. And finally, the other big thing is I think there are a lot of opportunities for actually increasing food productivity using AI, information technologies, and CS. And so that's another very exciting areas where I think we're going to see a lot more work in the coming years, like precision agriculture, finding more effective ways to manage the fields, better models to deal with pests and more effective seeds. All sort of interesting questions that I think we can play a role in as a community to improve the situation. Some of the work we've been doing in my group has been on trying to come up with good models to make crop yield predictions. So try to figure out, again, in an expensive and scalable way, what will be the production level for different types of crops, like corn or soybeans in different parts of the world. And this is a very important problem. You can think of it both at the sort of state level, trying to predict, or at the country level, how much of a particular type of crop will be produced by a country in a given year. You can also even more, it's even more useful if you can do it at the county level, sort of like you can predict how much each county in the United States will produce of different types of crops. And even more effective would be a kind of model that works at the field level. You can actually predict variation within fields because of soil properties and elevation and topography and all sort of things. The idea is that we want to do it using, again, cheap, passively collected, inexpensive, publicly available data. So we want to do it using remote sense data, so similar to what we did before for the poverty mapping project. In this case, we're going to use multispectral images, so images that are not sort of the standard RGB, but they also contain additional bands, near infrared or other bands that contain additional information on the locations that are surveyed by the satellite. And the goal is to build a model that will predict the agricultural yields for different crops by looking at sequences of these multispectral images over time for a particular location. This is a problem that has been studied before in the remote sensing community, and the typical approach is based on this pipeline where one starts with these high-dimensional complex objects, which are basically sequences of images over time, and then they extract the features by hand that are sort of handcrafted, like NDVI, EVI, NDWI. So features that domain experts think are going to be predictive of the kind of outcomes that they care about. So that they capture things like vegetation growth or water content or things like that. Then what they do is they build simple regression models to make predictions at different locations. Now, this pipeline has two limitations. The first one is that it's based on handcrafted features. And we've seen before that one of the big lessons that we learned in the past few years from the deep learning revolution is that we should not be using, like in a lot of domains, you can have huge improvements by getting rid of handcrafted features and instead training some kind of deep model that will try to identify which features are going to be useful for making the prediction. And the second problem is that it does not take into account the spatial structure, makes predictions independently at each location, like we saw before, and so there is room for improvement also in that space. So one thing we did was to try to again use a deep learning model to solve this problem. The first challenge that we encounter is that again we don't have a whole lot of training data available. So what we did is we came up with a dimensionality reduction technique to take these sequences of images and reduce them to histograms that are easier to deal with. They are still images, they're still relatively high dimensional, but they are a little bit easier to deal with. So in particular, what we do is we simply, for each location, we check over time, we bin different spectral bands, and we, over time, count the number of pixels that correspond to different intensities of different spectral bands, and we come up with these histograms. And although we lose some information here by doing this operation, you can see that we still preserve some of the signal that is present in the data. So you see here different columns corresponds to different years where the yield was low, medium, and high. And you can see that the different bands show different patterns in the different years. So there is hope that by using some kind of pattern recognition, some machine learning model, we'll be able to pick up the signal and be able to come up with good predictions. So the next step of the pipeline after this dimensionality reduction technique is to use to train a convolutional neural network to make the prediction, and then include the Gaussian process regression layer, as we saw before, to actually capture the spatial correlation. The accounting for the spatial correlation turns out to be very important. You can see on the left the kind of models that the errors that the model makes in different counties in the US when it does not have the Gaussian process component. And you can see that the errors are spatially correlated. Like there are areas where most of the errors, like the model is always overestimating, and other areas, yeah, even here where it's also kind of overestimating all over in that area, areas where it's always underestimating, and things like that. And by including the Gaussian process component, we can sort of take that into account. The Gaussian process component will model things like soil properties, other things that are not necessarily visible in the images, but we know that they do have this kind of spatial structure. And by taking that into account, we can significantly reduce the spatial correlation of the errors, and we can actually improve the predictive performance of the models. Turns out that our approaches based on deep learning and sort of identifying features automatically are actually much better than existing techniques based on handcrafted features. So the techniques with handcrafted features are shown on the left in the column highlighted in blue. On the right, we see our approaches based on various types of neural network. We have a convolutional one. We also have like a recurrent neural network plus the Gaussian process component. And as you can see, the convolutional neural network one plus the Gaussian process component is the one that actually achieved the best performance, the one that has the smallest error, in this case, on average, across many different years. Here, I should say, we've looked at soybean production in 11 states in the US that account for most of the production. But the model is fully general. We've only used data that is sort of publicly available and globally available. We chose to use the US because we have reasonably good quality data on the production levels, so we have good labels, but potentially this approach is scalable worldwide. All we need to have are basically labels on the food production levels for different counties or different fields or different states over time. So it turns out that we can use this model to forecast yields ahead of time. So here we're showing the error that we make by using different models based on making predictions on the yield that we're going to have that year when we make the prediction in May, June, July, August, September, and October. And as you can see, all the models get better and better over time because we just have more data. And as expected, as you can see, our neural network models are actually improving over existing techniques. And it turns out that when we make predictions, we compare to the kind of predictions that USDA makes in August, September, and October. And in August, we're actually able to improve over USDA predictions. This is significant because USDA actually does surveys in the fields. They go out, they check the size of the beans, and they check the sample fields and how healthy the plants are. And we can actually do better, at least in August. We don't do better in September and October, but in August, we can actually do better. And we just use remotely sensed data, which is impressive because it's scalable. We can potentially apply it to different countries as well. This one I can skip this. How much it improves using weather. As future steps, there are a number of directions that we are excited about. Of course, we want to scale these models, both the poverty ones and the yield ones, the food security ones, to the entire globe. Something we think we can do, and we're working on. One of the things we're pretty excited about is to use new data sources. We have a collaboration going with Planet Labs. That's a startup here in the Bay Area that is producing these tiny satellites that you see one there, held by their CEO, by Will. And these satellites are very, very inexpensive. They're really taking on governments with their operation, and they can provide reasonably good data, like 2-3 meter resolution images. And because they are so inexpensive, they can get a kind of coverage that is was just not possible before. They plan to be able to cover the entire world at every day, like 2-3 meter resolution by the end of next year. And so you can imagine that this kind of data contains so much information that if only we had ways to actually extract these insights and figure out really what is changing, what is going on from these images, we could really be able to sort of track the health of the planet in real time. And so we're pretty excited about what we can do with this type of data. Some of the things we've been looking at are predicting different kinds of outcomes. For example, food prices. That's another thing for which there is data available. There are other startups that are working on collecting data using crowdsourcing and mobile platforms. So we've been talking to them to see whether we can combine these new unconventional data sources and come up with useful models. Field level predictions, that's another thing for which we know we can build reasonable models. You can see one here. Unfortunately, the data is not publicly available, so these studies are difficult to reproduce. This was provided by insurance companies, but they don't want to share the data. And so we are thinking about ways to do this using publicly available data, because that would be huge if we had access to this kind of models that can predict at the field level what's the yield that is we're going to achieve for that location. So to conclude briefly, I think the other exciting direction is to figure out how to use these models, these predictive models, to help us make better decisions. One example where we show how to do that is on using yield models to actually improve food productivity. One team from our team participated in the Syngenta Crop Challenge that was held at Informs last year. And basically the challenge posed this problem of trying to identify which combination of different soybeans you should plant in a given location in order to maximize the yield. And they provided a lot of very high quality, lab quality data on the historical yields of different soybean varieties under different sort of weather condition and soil properties. What we did was to construct another type of yield model using an ensemble of different machine learning techniques that I'm not going to describe, but it's sort of not too different from the kind of model I talked about before based on remote sense data, except this one is much more accurate because it's using high quality lab data that was provided by Syngenta. Syngenta is a big multinational corporation, multi-billion-dollar corporation working in the agrochemical business. Then we came up with an uncertainty model that basically captures the different weather conditions and weather patterns, and we put them into an optimization framework that essentially tries to find the combination of different varieties that one should use in order to maximize the expected yield, while at the same time being somewhat risk averse. So you want to make sure that we want to somehow minimize the variance that we have on the actual on the yields that we're going to get, so that we don't have too much risk based on the kind of portfolio of seeds that we use for that particular time. Turns out that this model won the first prize, and so we're pretty excited about using these kind of ideas with the other yield models that we constructed based on remote sense data, because that could really be pretty huge if we're able to extend it and apply it, say, in other developing countries where these models could really have a big impact. So this was it. If you want to learn more about the kind of projects we have going on, please visit this website. We set up an interdisciplinary research group of people from computer science, earth system science, and to try to find good answers to these problems. This is joint work with a number of people, especially Neil, who is my PhD student, who did all the work and Michael on the poverty mapping, and Xiao Chang and Jeshuan on the crop yield work, and they really did a great job on building these models. And that's it. Thank you.
Well, thanks so much, Stefano. This was great. You don't get the full effect of applause across the many nodes, but that's all right. That's one of the costs of reaching the world. Are there any questions? You can post them on chat. You can post them on the Q&A. And if anyone is still thinking, I guess I have one. Or several, but it seems to me the approach to transfer learning, to use an old software engineering term, uses loose coupling between the way it communicates from the initial task. In your case, it's using a convolutional neural network to create a feature set that's then used to, I suppose, augment the data one could think of for the main task. And you could imagine, rather than using convolutional neural networks for that, you could use your favorite regression method to generate a prediction on, say, light level, using, say, regression trees and maybe some internal features using the regression tree, and try that method as the method for augmenting the data set for the main task. I mean, would you agree with that? And is there something, would you experiment with different methods for generating those feature sets?
It's definitely a good idea. I think it would be worth trying. We went for the CNN one, but it's definitely it's entirely possible that there are other kind of features that you could discover using other kind of regression models. I think CNNs are particularly suitable for these kind of tasks because of the kind of inductive bias that you put in when building these models, like the fact that you're using convolutional kernels sort of enforces the fact that you're looking for features that are translational invariant, so which is kind of something that we would like to see. So you're sort of using prior knowledge in the way you're constructing these neural networks, and that's a big plus. The other big plus is that you can train them relatively efficiently doing stochastic gradient descent and using GPUs. Like, using GPUs is key to actually training these models. Like, it would take an incredibly long amount. It takes days on a GPU. It would take forever to do it on CPUs. So it's actually, I don't know how feasible it would be to train different kind of machine learning models on the on the kind of extremely large data set that we need in order to capture all the different variation that we have in these types of images.
Okay, very good. So we have a question from Jacob Zietler. It was mentioned that there are nowadays plenty of freely available satellite data. Is this data of sufficient quality? Is there a significant increase in classification performance with commercial data?
So the data we used actually is publicly available. It's pulled from Google Maps. So we know that there is better data available for sure, like to intelligence agencies. They have access to much higher quality data, but the publicly available data is already good enough to do all sorts of interesting stuff.
Okay, very good.
The only thing that publicly available data doesn't have is the kind of spatial resolution, temporal resolution that we would like, that, for example, Planet Labs is providing, like images every day, or maybe multiple images during a day, or like a high resolution video. That's not something that you currently have with publicly available imagery.
Okay, very good.
From kernel.
Hi, question from here. What do you know about where the model does not predict well? So you've looked at sort of these countries in Africa, and sometimes it predicts better than others. What is missing, do you think, or what aspects make it harder to predict?
Good question, yeah. So we know that.
I have a related question, so maybe then you combine. Did you try your models on developed countries, for example, in the US, where the landscape in terms of poverty is completely different?
Good question, yeah. So we know that a lot of the predictive power of the model comes from the fact that it's able to separate the rural areas versus like urban areas. We know that the urban areas are particularly hard for us. I think it's because you cannot really, just by they sort of all look the same, and it's very hard just by looking at the buildings to figure out whether the areas are rich or not. And I think that would be the case also in the US. I would imagine that it would be quite hard to make predictions on income based on satellite images in urban areas. But that's something actually I think would be fun to do. It's one of the projects that we've been trying to push, try to basically predict housing prices using the images. Like Zillow has an API publicly available. You can just pull prices, and so we just wanted to see it, to train and see whether it works. We haven't done it yet, but I think it would be. I was also curious to see whether it would work, because I don't know, to be honest.
Very good.
So, but Stefano, did you try these models on developed countries? Not at all.
Yeah, kind of.
Yeah, I mean, just curious about that.
Okay, thanks.
Are there other questions? Well, Stefano, we've kept you online for quite a while. We really appreciate your presentation. It was great, and this has been recorded, and we'll probably send around permissions to upload it. But it's so others can enjoy it. Any parting words, Cornell?
Well, thanks a lot. This is very exciting. Keep up with the good work. And, we want to extend this seminar. If there are people interested with topics, ideas, please email us. And this is really an open forum. And thank you, Stefano. And again, thank you, Christian and Doug, for organizing this.
Thanks for inviting me.
Thanks, everybody. And we will email people regarding the next seminar. And remember, it will be on the website as well. But Stefano, thanks again. And so long, everybody.
Bye-bye.
Bye.